Hello, this is the second part of the video for chapter 11. And in the last video, we built a growth model and we looked at the relationship between saving and the standard of living. So we had a model where we had capital per person on this axis, output per person on this axis. We put in a line that captured depreciation, delta K over N, depreciation per person. We're normalizing by N. We put in the production function, F of K over N. And then we put in savings equals investment, which we noted was SF of K over N. We can call this S0 for initial savings rate. That savings rate gives us a particular level of K over N, say K over N0. N's fixed, so I could write K0 over N as well. And if we bounce this off the production function, if we give the production function K over N, it gives us back Y over N. And so at this initial savings rate, we had a particular standard of living. And there's no growth. This is a stationary state. This is an equilibrium. Y over N is just a fixed number. So this is just zero growth. And the question was, well, if we increase the savings rate, what will happen? Will we get any growth? What will happen in the standard of living? Those sorts of things. And what we showed was that if we increase the savings rate to, say, S1 F of K over N, that will result in more capital accumulation. Our new equilibrium is here. We explained why that was an equilibrium last time. That's where K over N is stationary. So that would give us a higher capital per person. So we'd have more capital accumulation. And it would also give us a higher standard of living, a higher level. But after the adjustment, it would take some time. We'll talk, that's what we're going to talk about, is how long it's going to take to get from here to here. But after the adjustment, we'll get a little bit of growth in Y over N as we move from here to here. But after the adjustment, this is a new stationary state and there's no more growth. And so an increase in the savings rate does raise the standard of living, but it doesn't change the long-run growth rate. You get a spurt of growth as you move from one level to the other, and then it ends. Now, what the next part of the chapter is all about is figuring out some magnitudes. How big of an effect does a change in savings have on the standard of living? This move, when S went up, this went up. How big of an effect is there? How sensitive is it to the savings rate? And secondly, how long does it take? Is it a really fast process to get to that new standard of living? Or do we think it should be a relatively slow process? So what we're going to do is just take our model and parameterize it, put some numbers to it, and see what it tells us about these questions. How big the effect of a change in savings is, and how long it takes. So this is called, in the book, it's getting a sense of magnitudes, I believe. So what we're going to do, we've been using a general production function. Y over N is F of K over N, and we've been putting T's on these. We're going to use a specific case of this next. Let me just drop the T for simplicity. We don't need to carry them around for the moment. Let's take Y is equal to the square root of K times the square root of N. This is a Cobb-Douglas. You can also write this as Y equals K to the alpha, N to the 1 minus alpha. Since alpha is a half, alpha and 1 minus alpha are the same. So this is just our standard Cobb-Douglas production function. We know that this has constant returns to scale. If we double K and N, we'll double output. And we also know it has diminishing returns. We showed this earlier, to each factor. As we increase K, holding N fixed, Y goes up less and less for each additional unit increase in K. Same for N. As N goes up more and more and more, the effect on Y becomes less and less and less due to these diminishing returns. And so there's nothing new under the sun there. Let's put it into this form. All we have to do is divide both sides by N. So you've got room on your notes to come down here. I'm just going to erase. So this tells us that y over n is equal to k to the 1/2 times n to the 1/2 over n. But that just tells us that y over n is equal to k over n to the 1/2 from just basic algebra. This is just 1 over n to the 1/2. Pull it over there, and you're all done. So that's a specific case for this. And we can put the t's in if we want yt as a function. It depends upon kt over n to the 1/2 power. So that's our production function. We give this a kt. It gives us a yt back for a given n. So again, our production function that we're going to want to use, let me just write it over here so we have it, is yt over n is kt over n to the 1/2 square root. Now let's go back to our equilibrium condition, and that came from our capital accumulation equation. So if you remember, we said it must be the case that kt plus 1 over n minus kt over n is equal to sf of kt over n minus delta kt over n. This is investment, this is depreciation, the change in the capital, the difference between investment, the new stuff, minus what disappears due to depreciation. So this is the change in the capital stock from t to t plus 1. And we said at equilibrium, it must be that kt plus 1 over n equals kt over n. That's a stationary state. Those have to be the same. Kt plus 1 has to equal kt. So this is 0. So at equilibrium, what we know is that sf of kt over n has to be equal to delta kt over n. That's just where we find, when we've been doing this growth model, we have the delta kt over n, then we have the f, then we have sf. That's this. This is the equilibrium point. That's how we find the equilibrium point. It's where those two things are equal. So that's just what we've been doing graphically. All right? So all we need to do at this point to actually parameterize this thing is plug in this production function. This is f right here. This is yt over n. That's the production function in which we've done this. So we're going to plug that in. So now we know that s times kt over n to the 1/2 equals delta kt over n. All right? And this is output here. Y over n. Now I'm going to do what the book does. There's simpler ways to do this algebra than the way the book does it, but I'm going to go ahead and just do what they do. Let's square both sides to get rid of the square root. So s squared times kt over n equals delta squared times kt over n squared. And now we're just about what we want. Just about to the point we want to be at. So s squared over delta squared, just bring that under there. Bring that under there is kt over n. So s over delta, take the square root of that, has to be that to the 1/2. Kt over n to the 1/2. But look, that's just output, right? And so what we have is a relationship between the standard of living, s, and delta. So s over delta equals yt over n. And we're at the steady state, so it's this, put a star. I should have stars on all these. These are all steady state values. I did that in my notes. All these k's, once we started with these two, set these equal, should have had stars on them because these are all steady state values. So we'd be using star to indicate steady state. And you don't really need a t if it's steady. Okay, so what we have then is that S over delta is the steady state y over n. That's the standard of living. Now, some pretty reasonable estimates for this would be a savings rate of 0.10 out of income and a depreciation rate of 0.10. So what this tells us is that 0.10 over 0.10 equals y star over n. So it's equal to 1. Just using that. So we're not saying what the units are. This could be 1 million, 1,000, 110,000, whatever the units of y are measured in. We're not really talking about that. It's a nice normalization. It gives us 1. Now, what if, so you can think of this as S0. What if savings goes up to S1 equals 0.20, like we did graphically? Well, notice the standard of living would double because now y star over n would equal 0.20, the savings rate over the depreciation rate 0.10, which would be 2. And so the standard of living will have doubled if the savings rate goes from 10 to 20%. That's a huge effect. And so the point is that a change in the savings rate, according to this model, has a pretty darn big impact on the standard of living. If this was, just went up 5%, which isn't that large, from 10 to 15%, this would be 1.5 times. So savings has a relatively large effect on the standard of living. The next question is, how long would it take to go from y star over n is 1 to y star over n equals 2? It's not going to be instantaneous. We have this capital accumulation equation. So we have this equation we can use to see how long this is going to take. So this is called the dynamic effects of an increase in the savings rate in the book. So how long does it take? So we're going to use the equation kt plus 1 over n minus kt over n equals s f of k over n, but we know that's k over n to the 1/2, kt over n to the 1/2 square root minus delta kt over n. So what we're going to do is let the savings rate increase from 0.10 to 0.20 at time t equals 0. And then we'll look at what happens at t equals 1, t equals 2, and so on. In year 0, nothing will happen. We'll stay at the old steady state because it takes a year in the model. That's what this difference is. It takes a year for an increase in savings to cause an increase in investment and an increase in the capital stock. And so in the year this happens, the capital stock doesn't change yet. It's not going to change until the next year. Okay, so in year 0, y0, let me just do it over here, y0 over n equals 1.0, just like before. There's no change in the steady state. Now we can use this formula for year 1. So we know what happens in year 0, which is nothing. So now we can say, well, K1, this is when t equals 0, K1 over n minus k0 over n equals, and we can use this formula, equals 0.20, which is our new savings rate, times k0 over n to the 1/2 minus, that's 0.10, the depreciation rate, times k0 over n. Now we know that k0 over n is 1. Remember that y over n is the square root, or I've been using 1/2, same thing, k over n to the 1/2. If this is equal to 1, then that has to equal 1. So k over n is 1 in this. So this tells us we want to know what k1 over n is. We know what k0 is, so k1 over n minus 1 is 0.20 times 1 to the 1/2 minus 0.10 times 1, because k over n is 1. So k1 over n is equal to 1 plus 0.2 minus 0.1, so it's 1.10. So y1 over n will be the square root, that to the 1/2 power of 1.10, which is, I wrote it down here somewhere, 1.04888, and so on. It's about a 5% growth rate in the very first period. So we found k1 over n. Now we can iterate again and find k2 over n. We know what k1 is. Now we can find k2 using this. So k2 over n minus k1 over n is s 0.20 times k1 over n minus delta times k1 over n. Well, we know what k1 over n is. So k2 over n minus 1.10 is 0.2. Oops, this is to the 1/2 power, times 1.10 to the 1/2 minus delta times 1.10. And if you solve this, k2 over n will be equal to 1.19976 and some more, approximately 1.20. So y2 over n will be the square root of that 1.19976, which turns out to be 1.095 approximately. That if you look at the growth rate, it's actually less than the first time. The growth rate's going to get smaller and smaller and smaller. So we could keep doing this. And eventually, if we go long enough, we'll get to 2.0. Because remember, the standard of living goes from 1. We did this an infinite amount of times over n. It's going to be 2.0. And so what we could do is we could graph the evolution of y over n over time. So we could look at what happens to y over n. So here's a graph with time on this axis. This is t equals 0. This is y over n. And at t equals 0, it was at 1.0. That's what we saw here. Then at t equals 1, it goes up to 1.05. At t equals 2, it goes up to 1.10 approximately. And so we could map out how this thing evolves until it finally asymptotically hits 2.0. If you do that, if you go out 10 years, here with 10, this number is 1.25. So after 10 years, only about 1/4. You're only a fourth of the way there. You've only gone to 1.25. So you're only a quarter of the way there. So the point is, this could take decades. It takes a long time for the standard of living to rise. This could be 30, 40 years before it actually doubles. And so according to this model, it's going to take a really, really, really long time for the economy to reach its new higher steady state. Let me redraw this with a little more compact, because I want to put another graph underneath it. So again, this is time. Here's 1.0. Here's 2.0. We start at 1, and we're going to end at 2. So the way this goes is it rises, and then it ends up asymptotically at 2.0. And as we saw a second ago, after 10 years, you're only to 1.25. And I didn't really write down the other numbers, but it's going to take a long, long time to get there. The slope of this curve is the growth rate. So if we were to look at the growth rate of y over n, that's the slope of this thing. It's going to start out steeper and get flatter and flatter and eventually hit 0. So the growth rate looks like this, and eventually asymptotes to a 0 growth rate when you hit this new steady state and stay there. So you start out with a high growth rate and you end up at a lower growth rate. If you look at this, for the first 10 years, the average growth, the average slope, if you're to take it at 9, 8, 7, 6, take the average growth rate, the average slope. Here are two of the growth rates. As I noted, this is smaller than this. This is about 5%, this is a little less. The average for the first 10 years is 3.1. The average out to the second 10 years is about, the average 3.1%. The average is about 1.5%. So the point is that this increase in the savings rate has an effect on the growth rate of y over n for a pretty long time. For 10 years, it goes up by 3%. For the next 20 years, it goes up by 1.5%. If you average over those, I don't know what it would be, about 2.25 or something like that for the whole 20-year period. So for 20 years, you'd get a much higher growth rate. Now, eventually, the growth goes to 0, but the increase in the savings rate does have a relatively long impact on the growth rate of the economy. It's not permanent. Eventually you hit 0, but it does take a long time to get there, according to the parameterization of this model. Okay, a couple more topics and we're going to be done with this chapter. Just one more after this. The other thing that the book looks at here is it puts some numbers to the U.S. saving rate. And I'm going to let you read this. I'm just going to summarize the results. And the golden rule. Remember, the golden rule was if you take the savings rate, it's 0. If you have no savings and no capital, you have no output. So crappy standard of living. This is consumption, sorry. If your savings rate is 1, so you have everything you produce is invested and nothing's consumed, C over n is 0. So it must be that there's some savings rate where C over n is maximized. And that's called the golden rule. Now, they put some numbers to this, and I used these numbers earlier when I first brought this up. This is about 17% for the U.S. according to their estimates. We're clearly below that. So we're clearly below the golden rule. And again, we say, well, why doesn't this society then, if we could have more consumption per person, why don't we choose to save more? Why doesn't the government put these incentives in place? And the answer is, this generation, remember this takes a long time to get to the new steady state, 30, 40 years maybe. If you increase the savings rate, this generation would do worse. The immediate impact is for consumption to go down, and then it rises to a new higher level over time. If you were to look at the time path of C over N, so this is time. So you have one savings rate in place, and C over N is at its steady state. And at this point, savings goes up. The immediate impact is for consumption to drop. Then it rises in the longer run, if you're on this side of the golden rule, to a new higher level. But the effect on this generation is that they're going to do worse. Future generations will do better. Well, future generations don't vote, and so this generation might be unlikely to put in politicians who would invoke policies that would cause them to lose consumption, even if it's going to make their kids better off. But in any case, whether that's the right story about why it doesn't happen, it does appear that we're far below. This is closer to 10%, depending on what time period you look at. It was lower than that right before the Great Recession, but depending on when you look at, we're clearly below the golden rule level of savings, according to econometric evidence. Okay, one last thing. We've talked about physical capital, K, but there's another type of capital that we need to worry about, and that's human capital. Basically, that's your stock of knowledge, how much stuff you've learned over time. So, you know, skills and knowledge and knowing how to do things clearly makes a difference for output. That's where technology comes from. So somehow we need to get human capital into the model. I mean, we know that as capital goes up, product output goes up. As human capital goes up, we're going to call that H, productivity goes up, and that's also going to cause output to go up. So we need to get this into the model somehow. And it's also had a big change over time. At the beginning of the Industrial Revolution, only 30% of people could read in the OECD countries, those are basically the developed countries. And today it's about 95%. So there's been a huge increase in the stock of human capital over time. And we'd like some way of characterizing it in our growth models, how that's affected things. And we're going to do that. So how do we get human capital into the model is the question. What we're going to do is just what we did before. We're going to say y is some function of capital, labor, and we're going to add human capital and say that matters. For a given stock of capital and a given stock of labor, the bigger H is, the more knowledge and technology we have, the bigger Y will be. If we assume, as we will, constant returns to scale, we can write this as Y over N is some function of K over N and H over N. So output per person depends upon the capital per person, physical capital per person, and human capital per person as well. All right, so how does this change the model? How does this change the result? It doesn't really, it just extends them. So how does it change the results we've seen so far? First, let me get these in order so I get them the same way the book does. Claims about the effect of capital, physical capital per person going up remain valid. They're the same as before. When S goes up, K over N goes up, and that causes Y over N to go up, but no long-run effect on growth. You just go up to a new steady state. That result extends to H over N. When H over N goes up, Y over N will go up to a new steady state, new equilibrium, and there's no long-run impact on growth. Okay. So, the standard of living, which we're measuring as Y over N, depends upon two things. How much society saves, that's where K comes from, and how much society invests, sort of another way to save, in education. That's where H comes from. And the last point we want to make, you say, okay, then, if they both cause the standard of living to go up, which one's more responsible? And so studies indicate K and H are approximately equally responsible for determining the standard of living, Y over N. Those results are hard to quantify. There's a lot of uncertainty. But, you know, if you had to nail people down, that's probably what they would say. Now, there's one last topic in this chapter called endogenous growth. And what is that all about? So far, the only way, so the previous, what we just did, says K over N up or H over N going up alone, by themselves, alone, causes Y to go up, but there's no long-run effect on growth, no long-run impact on growth, right? That claim's been challenged to some degree, and it's been Lucas and Romer's and others. Individually, these things have diminishing returns, but what if they somehow could grow together? And models of endogenous growth really have that feature. These two things grow together. So what these models sort of say is the following, that Y over N depends upon both K over N and H over N, Both can be accumulated over time. Knowledge can grow, physical stock of capital can grow. But they do not have a permanent effect on the growth of y over n. However, I'm going to erase so I can write it more clearly. So y over n depends upon both k over n, both can be, and h over n, both can be accumulated, but you don't have a long run effect. Pause and rewind if you need to. But, however, the above is for a given level of technological progress. If, when we invest in education, when our human capital grows, that causes technological progress to increase, that can have a permanent effect, permanent impact on economic growth. And what that does is it takes us to the next chapter, because that's precisely what the last chapter that we're going to cover is all about. Technological progress and how that impacts growth. And we'll also add population growth back into the model at the same time. Thank you.